Tonight, we are going to dismantle an image that has been sitting quietly in your mind since you were a child. A single dot floating in a great, silent dark. A sudden flash, and a universe rushing outward, star by star, into an emptiness that was already waiting for it. It is one of the most familiar pictures in all of science. It appears in almost every textbook, every documentary, every classroom animation you have ever seen. And it is, in almost every detail, profoundly wrong. Because tonight, we are not going to ask what banged. That is the small question, the comfortable one. We are going to ask something far stranger, something that has haunted the sharpest minds in physics for more than half a century. A question so quiet and so vast that it may follow you into your sleep. Can a universe truly be born from nothing? And if it can, what on earth do we mean when we say that word? Nothing. For the next 2 hours, we are going to walk backwards through everything you were told about the beginning of the universe. Slowly, carefully, layer by layer. We are going to find that the Big Bang was not an explosion, and that there was no dark room for it to explode into. We are going to find that the word nothing hides at least 3 completely different meanings, and that physicists and philosophers have been quietly arguing about them for over 100 years. We are going to sit with a strange metal experiment in a laboratory in New Mexico that measured a force coming out of absolute emptiness to a precision of less than 1%. And it will make you wonder if empty space has ever really been empty at all. Then we are going to meet a very strange idea. An idea written down on a single page in 1973 by a physicist so quiet in his profession that when he first spoke it aloud, everyone in the room thought he was joking. The idea was that our entire universe, everything you have ever seen or touched or loved, might be a quantum accident, a hiccup, a bubble that should never have appeared, and that should have vanished in an instant back into the silence. And then, it gets worse. Or better, depending on how you feel about your certainties, because we are going to arrive together at what many physicists now call the worst theoretical prediction in the entire history of science. A prediction about the energy hiding inside pure emptiness. A prediction so wrong, so catastrophically off from what we actually measure, that if you laid its error out digit by digit, you would need more zeros than there are atoms in every star, in every galaxy we have ever counted. And in the last 2 years alone, 3 of the largest telescopes ever built have started quietly sending back data that suggests the mistake may run even deeper than that. That we may have been measuring the very fabric of the universe wrong from the very beginning. By the end of this night, you may find that the question we started with, the one you have carried in some quiet corner of your mind since you were small, was not simply unanswered. It was never a real question at all. Before we go any further, if you find yourself drawn in by this kind of slow, patient exploration of the cosmos, a quiet like or a subscribe genuinely helps this channel keep making these long journeys into the dark. It is a small thing on your side, but on ours it makes an enormous difference. Now, let us begin. Close your eyes for a moment if you can and picture the image you were given. Perhaps you see it as a diagram in an old school book. A tiny bright point sitting in the middle of a black page, little arrows shooting outward from it, a caption underneath reading the birth of the universe. Perhaps you see it as a scene from a film. A great fireball ballooning out into a starless void, seeding the darkness with the first galaxies. Whatever version you carry, notice something about it. Notice that in your picture there is always a room, a background, a dark, empty stage on which the drama happens. That is the first illusion. There was no stage, there was no dark, there was no outside. Wherever you place your imaginary point of beginning, you are already assuming the very thing that had not yet come into being. You are placing something inside nothing, and that is where the entire mystery begins. Because if there was no room for the universe to appear in and no darkness for it to expand into, then whatever happened at the beginning did not happen somewhere. It did not happen inside anything. And the deeper we look at that idea, the stranger it becomes. Because a beginning without a somewhere is a very difficult thing for a human mind to hold. We are creatures of place, of before and after, of edges and rooms. We do not know how to imagine an event that has no location. And yet that is exactly the puzzle we are going to sit inside together tonight. So let me ask you something before we take the next step. When you were young and someone first told you about the beginning of the universe, what did the moment before it look like in your mind? A darkness, a silence, a blank page waiting to be written on. Take a moment, if you like, to leave your answer below, because that image, the one you have quietly carried since childhood, is exactly what we are about to take apart. And to take it apart properly, we have to go back to the story you were told. The tidy story. The one that begins with an explosion. Because before we can understand why the universe might have come from nothing, we first have to understand very precisely what the universe actually is, and what, more importantly, it is not. The story you were told begins almost always with a bang. It is such a familiar word that we rarely pause to notice how strange it is. A bang. A sound, a concussion in the air, the rupture of something confined spilling out into a room. That is what the word means in every ordinary sense. And that is exactly the picture it plants in the human mind. But here is a small, disquieting fact. The name Big Bang was not chosen by the man who proposed the theory. It was invented by a man who despised it. His name was Fred Hoyle. He was a British astronomer, brilliant, sharp-tongued, and utterly convinced that the universe had always existed. In 1949, on a BBC radio broadcast, he was trying to describe a rival theory, a theory he found absurd, a theory that said the entire cosmos had begun in a single moment from a single point of unimaginable density. And to mock it, he called it, in passing, this Big Bang idea. He meant it as an insult. The name stuck. It stuck so thoroughly that for the rest of the century, and into our own, almost every human being alive would grow up carrying that exact metaphor in their head. A firework in a dark theater, a grenade in an empty room. And almost every human being alive would be wrong, because the theory Hoyle was mocking does not describe an explosion, not in any ordinary sense of the word. There was no fireball flying outward into a waiting darkness. There was no shockwave rippling through some pre-existing air. There was no observer standing at a safe distance watching the cosmos ignite. There was no distance. There was no air. There was no room. What we call the Big Bang was not something that happened inside space. It was something that happened to space. It was the expansion of space itself. Let that sit for a moment, because that single sentence quietly overturns almost every mental image you have ever been given of the beginning of the universe. If space itself was expanding, then there was no outside for it to expand into. There was no dark stage. There was no elsewhere. Every point that exists today, every star, every galaxy, every atom in your body was already present at the beginning, not gathered in a small dot in the middle of an empty cosmos, but smeared uniformly across all the space there was, which at the very beginning was infinitesimally small. Not because it was a tiny ball sitting in a big void, but because everywhere was tiny, everywhere was compressed, everywhere was hot. There is a subtle but important difference between those two pictures, and it takes a while for it to sink in. In the wrong picture, the one you were given as a child, the universe is a firework rising into an empty sky. In the right picture, the sky itself is what is unfolding. You are, right now, inside that unfolding. There is another way to feel this. Imagine an ant walking on the surface of a balloon that is slowly being inflated. Every point on the surface of the balloon is moving away from every other point, not because the ants are running away from a center, but because the fabric they are standing on is stretching underneath them. If you asked one of those ants, where is the center of this expansion, it could not point to any place on the balloon, because the center, if there is one, is not on the surface at all. Our universe, as far as we can tell, is like that surface. Only in 3 dimensions instead of 2. There is no center we can point to. There is no edge we can walk to. Every galaxy is racing away from every other galaxy, not because they are hurtling outward through space, but because the space between them is quietly, endlessly stretching. Which means if we run the clock backwards, we do not find a single point where the explosion began. We find a moment where the stretching had not yet begun. A moment when everything, everywhere, was almost impossibly close together, almost impossibly hot, and almost impossibly dense. That moment is what we mean in the language of modern physics by the Big Bang, not an explosion, a beginning of the stretching. We know this is not a fantasy. We know it because the universe left us evidence. Beautiful, patient, slow-cooling evidence that is still arriving at our telescopes right now tonight as you listen to this. In the 1920s, an American astronomer named Edwin Hubble, working with a great new telescope on Mount Wilson in California, made a discovery that broke the previous century. He noticed that almost every galaxy he could see was moving away from us, and the farther away it was, the faster it was moving. The relationship was not random. It was clean. It was linear. It was the kind of pattern nature reserves for its deepest laws. There is really only one honest interpretation of that pattern. Either we happen to sit at the exact center of a cosmic explosion, which would be a coincidence so absurd we can safely dismiss it, or space itself is expanding everywhere at all times. And every observer on every planet in every galaxy would see the same thing we do, their neighbors drifting away, their skies growing quieter century by century. The second answer turned out to be correct. And if the universe is expanding today, then in the past it must have been smaller and denser and hotter. Run that clock back far enough, and you eventually reach a point where the entire cosmos, everything that would one day become galaxies and gas clouds and human beings, was compressed into a state hotter than the interior of any star. A state so hot that atoms could not hold together, a state so dense that light could not travel freely. That was the early universe, not somewhere in it, all of it. And here is where the evidence becomes almost unbearably beautiful. If the early universe really was that hot, then at some point, as it cooled and expanded, it should have crossed a very specific threshold, a moment when it became cool enough for the first stable atoms to form. And in that moment, light, which had been trapped and scattered like a fog for hundreds of thousands of years, was suddenly free to travel, to stream outward in every direction into the growing darkness. That light would still be around today. Stretched, cooled, faded almost beyond recognition by billions of years of expansion. But it would be there, a quiet, uniform whisper arriving at every point in space, from every direction at almost the same temperature. A faint microwave hiss filling the entire sky. In 1964, two engineers at Bell Laboratories in New Jersey, named Arno Penzias and Robert Wilson, discovered exactly that. They were trying to build a sensitive radio antenna, and they kept picking up a strange, uniform background noise. They cleaned the antenna. They shooed away the pigeons roosting inside it. They checked their instruments over and over. The noise did not go away. It came from every direction in the sky at every hour of the day. They had, by accident, become the first human beings to hear the afterglow of the beginning of the universe. We call that afterglow the cosmic microwave background, and the temperature of its whisper is remarkable, 2.7 degrees above absolute zero. So cold that it would freeze anything you can imagine, and yet warm enough and uniform enough and consistent enough that no other explanation for it has ever held up. That whisper has now been mapped in exquisite detail by 3 generations of satellites: COBE in the early 1990s, WMAP in the 2000s, and most recently, the Planck satellite, whose full mission ran from 2009 to 2018. Planck measured the temperature of that ancient light at every point in the sky, across the entire celestial sphere, to a precision so fine that if you plotted its variations on the surface of a calm ocean, most of them would be smaller than a single ripple. And embedded in those tiny ripples is a full portrait of the infant universe, the age of the cosmos, 13.8 billion years, give or take about 20 million. The proportion of ordinary matter, and dark energy, the rate of expansion, the geometry of space itself, which appears to be almost perfectly flat, in the same way that a football field is almost perfectly flat, even though the earth beneath it is curved. All of this from a whisper in the sky. So when we say the Big Bang, we do not mean a firework. We mean a fingerprint, a moment we have not seen but whose signature we can read in the faint microwave hum arriving at your rooftop right now. And yet, for all the beauty of that evidence, there is one thing it cannot tell us. The one thing we most want to know. It cannot tell us what happened before. Because if you keep running the equations backwards past that moment when the first atoms formed, past the hot, dense plasma, past the fraction of a second when the universe was a soup of quarks, and light, you eventually arrive at a point where the mathematics simply stops giving sensible answers. The equations produce infinities, temperatures with no upper bound, densities that outstrip meaning. A moment where every quantity we can calculate goes to a value that reality is not permitted to have. Physicists have a name for that moment. They call it a singularity, but the word is misleading. A singularity is not a physical object. It is not a tiny dot sitting somewhere in a diagram. It is a signal from our own equations that they have reached the edge of what they can describe. It is a flag, a warning light. A mathematical way of saying, whatever is happening here, our theory is no longer the right tool to describe it, which means the Big Bang, as it is normally taught, is not really the beginning of the universe. It is the beginning of our ability to talk about the universe. It is the point where general relativity, our best theory of space and time, quietly hands us the pencil and admits, I can go no further. What lies on the other side of that limit? What was happening in the moments, or the something that was not quite moments, before the equations began to work? That we do not know, not for certain, but we have ideas, very strange, very old, very beautiful ideas. Ideas that begin with a word we thought we understood, the word nothing. So before we take another step, let me sit with you for a moment quietly. Because you have just been asked to hold something very difficult in your mind, a beginning that was not in a place, an expansion that has no center, a universe that is not sitting in a larger emptiness but is the emptiness unfolding. Have you ever tried to picture something that has no outside, no edge, no further? And did your mind at some point quietly refuse, slide sideways, reach for a metaphor that turned out to be a lie? That is not a failure of intelligence. That is what it feels like to bump against the outer wall of what human imagination is built for. And if that thought comforts you or troubles you in some small way tonight, I would love to know which one when you have a moment. Because that limit, the one your imagination is bumping against, is exactly where we go next. We have taken away the room. We have taken away the darkness. We have taken away the stage. Now we have to look very carefully at what is left. At the word we use for it. At the word we have been throwing around casually for centuries as though we understood it. The word nothing. You will find over the next hour that it is not one word at all. It is at least three. And when you learn to tell them apart, everything about the origin of the universe, every question, every answer, every certainty, begins to look different. Let us go and meet them. Say the word out loud slowly if you like. Nothing. It is one of the smallest words in the English language. 2 syllables, 6 letters, and yet it hides more confusion and more disagreement and more quiet philosophical warfare than almost any other word in science. Because when a physicist says nothing, they very often do not mean what you or I mean when we say it. And when a philosopher says nothing, they almost never mean what a physicist means. And when a poet says it, they mean something else entirely. For most of human history, the confusion did not matter very much. Nothing was simply nothing, the absence of stuff, an empty jar, a dark room after the candle has been snuffed out, a silence between 2 sentences. But in the 20th century, that quiet, tidy word cracked open. And out of the crack came at least 3 different meanings, each pretending to be the same word. Let us walk through them gently, because we cannot ask whether the universe came from nothing until we know which nothing we are talking about. The first meaning is the one you probably carry in your head. Nothing as empty space, a vacuum, a region with no matter in it. If you pumped all the air out of a jar and all the dust and all the water and set it in a cold, quiet corner of a laboratory, and then said, "Look, there is nothing inside," that is the first kind of nothing, the everyday kind. The kind we can almost imagine. The second meaning is stranger. It is the physicist's nothing. Empty space with no matter, no radiation, no fields turned on. Not just an empty jar, but a jar in which even the possibility of energy has been drained. A pure geometrical container, holding nothing at all. This is a much harder thing to imagine, because it requires you to remove not just the visible content of space, but the invisible content too, the electromagnetic field. The quantum fields that fill every point of the cosmos, whether or not there is a particle riding on top of them. And the third meaning is stranger still. It is the philosopher's nothing, not just empty space, but no space. No time, no laws, no mathematics, no wave function, no possibility, the complete absence of everything, including the framework in which everything could ever exist. 3 different nothings. And when someone tells you the universe came from nothing, the entire meaning of that sentence depends on which one they picked. Now here is where the story starts to bend in on itself. Because in the last 100 years, physicists have discovered something extraordinary about the first kind of nothing. The everyday kind. The empty jar in the quiet corner of the laboratory. They have discovered that it is not empty at all. Turn your attention for a moment to the space around you. The air in front of your face if you are somewhere with air. Or the vacuum of the room you are in if we imagine we have swept it clean of every atom. The space that seems, by every measure of ordinary experience, to be simply empty. According to the deepest theories in physics we have, that space is not still. It is not silent. It is not sleeping. It is quietly seething with a kind of energy that is not there in any classical sense and yet is measurable, persistent, real. That energy has a name. We call it the vacuum energy or the zero-point energy. And it comes from a very old, very strange principle of quantum mechanics, first written down in the 1920s by a young German physicist named Werner Heisenberg. Heisenberg noticed something odd. In the world of the very small, you cannot know everything about a particle at once. If you measure its position very precisely, its momentum blurs into uncertainty. If you measure its momentum very precisely, its position slips away from you. The two quantities are locked together. Nature will let you know one or the other very well, but never both perfectly at the same time. This is not a statement about our clumsy instruments. It is a statement about the world itself. Reality, at its finest scale, refuses to hold still, and that refusal has a consequence. If a region of space had zero energy and stayed exactly at zero, then in a sense you would know too much about it. You would know its energy, and you would know it forever. Nature does not permit that kind of certainty. So even in the calmest, coldest, emptiest patch of vacuum you can build, energy is quietly fluctuating. Particles are appearing and disappearing. Fields are humming below the threshold of your instruments. The vacuum is not still. It cannot be, not without breaking one of the deepest laws we know. Which raises a very reasonable question. If all of this is happening invisibly in the emptiness around you, how do we know it is real? How do we know we have not simply invented a bookkeeping trick, a mathematical decoration that has no consequences in the actual world? The answer is the most beautiful little experiment I know. In 1948, at Philips Research Laboratories in the Netherlands, a Dutch physicist named Hendrik Casimir was quietly trying to solve a nagging problem. He was studying the forces between small particles in liquids, and he could not quite make the numbers work. In conversation with the great Danish physicist Niels Bohr, Bohr made a passing suggestion. Perhaps, he said, the answer had something to do with the fluctuations of the vacuum itself. Casimir went home, he did the mathematics, and what he wrote down was so strange, so quietly audacious, that even he seemed cautious about it. Imagine, he said, two flat metal plates, uncharged, perfectly parallel, held in the vacuum, almost touching, with a gap between them so narrow that a wavelength of light could just barely fit inside. Now think about the vacuum energy, the invisible hum of fields filling all of space. Outside the plates, that hum is unrestricted. Every possible wavelength of field vibration is allowed. Inside the plates, though, the geometry is constrained. Only certain wavelengths fit. The plates act like the walls of a very narrow organ pipe. Some notes can be played, some cannot. The result, Casimir calculated, is that there is slightly less vacuum energy between the plates than outside them. Very slightly. Almost impossibly slightly, but not zero. And that difference, that tiny asymmetry in the invisible energy of empty space, should push the plates together. Nothing, in other words, should exert a measurable force. For decades, the prediction sat in journals. It was too small to test with the instruments of the mid-20th century, and for a long time, some physicists quietly suspected it might be an illusion of the mathematics, a ghost. Then in the 1990s, technology finally caught up. And in 1997, a physicist named Stephen Lamoureux, working at Los Alamos National Laboratory in New Mexico, built an exquisite apparatus. Tiny, gold-coated surfaces, suspended on a torsion pendulum, isolated from every conceivable source of vibration and noise. And he measured the force between them. The prediction held, almost perfectly. In the years since, the experiment has been refined and repeated by teams around the world. Modern measurements confirm the Casimir force to better than 1% precision, not as a theoretical curiosity, as a physical fact. Two uncharged pieces of metal, sitting in what we used to call empty space, attract each other for no reason our old physics could explain. The only thing pushing them together is a slight imbalance in the invisible energy of the vacuum itself. Nothing, it turns out, pushes on things. There are other clues, too, that the vacuum is not quite as vacant as the word suggests. There is a phenomenon called the Lamb shift, first observed in the late 1940s by Willis Lamb and Robert Rutherford. When they measured the energy levels of a single electron in a hydrogen atom, they found that its behavior was slightly, persistently different from what the equations of the day predicted. The difference was tiny, but it matched, with astonishing precision, the calculation that assumed the electron was being gently jostled at every moment by the invisible fluctuations of the surrounding vacuum, as though the empty space around it were quietly nudging it over and over, and its energy carried the fingerprint of those nudges. And there is the spontaneous emission of light from excited atoms. Every fluorescent bulb, every neon sign, every distant star whose light you can see with your own eyes, is glowing because atoms in it are dropping from higher energy states to lower ones. In a purely classical universe, those atoms would have no reason to make the jump. They would simply sit there, in their higher state, forever. What triggers the jump in the modern picture is the perpetual presence of the vacuum fluctuations around them. The atom is not really alone. It is nudged, encouraged, prompted by the invisible hum of the field it lives inside. And it falls and it emits a photon. And the entire visible universe you have ever seen in some deep sense is lit by nothing. Take a moment, if you like, with that thought. Every candle you have ever lit, every screen you have ever stared into, every star you have ever wished upon, all of them are glowing because the vacuum of space is not really empty. Because the word nothing, in the deepest theory we have of the small world, is a lie of language. There is no place in this universe where energy has been permitted to fall completely silent, which brings us back to our original question and makes it much stranger. Because if the vacuum has energy, then that energy should have gravity. Every form of energy in Einstein's picture of the universe curves space around it. If the emptiness of space is quietly humming with energy at every point, then that hum should have an effect on the shape of the cosmos itself, on its expansion, on its geometry, on its long, slow history. We will come to what that effect is later. And we will come to the mind-bending mistake we have apparently made in trying to calculate it. But for now, hold on to this. The first kind of nothing, the everyday empty space, is not empty at all. It is a restless, glowing, quietly powerful thing. It pushes on metal plates, It nudges electrons. It lights up stars. Which means that when a physicist or a philosopher or a friend at a dinner party tells you that the universe came from nothing, you now have an entirely new question to ask them. Which nothing did it come from? Because if the answer is the first kind, the vacuum kind, then it is not really a story about creation from nothing. It is a story about the universe emerging from a very rich, very active, very energetic something that just happens to look empty to human eyes. And a universe that emerges from a bubbling quantum sea is not the same as a universe that emerges from absolute non-being. If the answer is the second kind, the physicist's stricter version, empty space with no fields at all, then we are in stranger territory still, because it is not clear that such a state is even physically possible. Every theory we have of the vacuum insists that the fields are always there at some level. A vacuum with no fields is not the ordinary vacuum. It is an abstraction, a mathematical suggestion, perhaps a limit that reality never actually reaches. And if the answer is the third kind, the philosopher's nothing, no space, no time, no fields, no laws, then no experiment we can perform and no equation we can write is really up to the task of describing where the universe came from. Because every experiment and every equation already assumes a stage, a setting, a backdrop of mathematics inside which the story is allowed to happen. To speak about a universe emerging from true philosophical nothingness is to speak about a universe emerging without any of the tools we normally use to describe emergence at all. That, roughly, is where cosmology has been stuck for about 100 years, sitting on a fence between three different meanings of the same small word. And yet, there is a thread, a thin, luminous thread running through the confusion, a thread that begins with the discovery that the vacuum is not empty, and leads, if you are willing to walk it slowly, to one of the most audacious ideas any human being has ever written down. Because if the empty space around you right now is quietly seething with energy, if the vacuum is not silence but suppressed music, then the leap that some physicists began to make in the middle of the 20th century is not as strange as it first sounds. They began to wonder whether the entire universe might be, in some sense, a single loud note, a fluctuation that happened to hold, a hiccup in the vacuum that, instead of vanishing back into itself, somehow ran away, grew, cooled, and became galaxies and stars and small conscious creatures on small warm planets, asking themselves how any of this could have started. Before we go there, though, sit with a question, if you feel like it. If the empty space in the room you are in tonight is quietly humming with an invisible energy, if nothing is not really nothing, even in the calmest corner of a laboratory, does the word empty still feel honest to you when you use it? Does the world around you feel slightly more crowded tonight than it did an hour ago? I would love to hear what shifted, if anything did. Because now we come to the moment when a small, mostly forgotten physicist in 1973, in a small room at a small conference, stood up and said very quietly the thing that everyone thought was a joke. the thing that no one has been able to entirely dismiss ever since. The thought that our entire universe, everything you have ever known, every face you have ever loved, every star in every sky, on every world, in every galaxy we can see, might be nothing more than a single, extraordinary, statistically improbable quantum fluctuation of the vacuum. That is where we are going next. The year is 1973. The place is a small physics seminar room at Columbia University in New York City. A distinguished British cosmologist named Dennis Sciama is at the blackboard, giving a talk. The room is full of graduate students, postdocs, professors, ordinary people, having an ordinary academic afternoon. At some point during the question period, a soft-spoken American physicist named Edward Tryon raises his hand. And he says out loud into that quiet room a single sentence. Maybe the universe is a vacuum fluctuation. There is a pause. Then, slowly, people begin to laugh. Not cruelly. Just the polite, uncomfortable laughter of an academic audience that has decided a colleague has made an odd joke. Someone chuckles. Someone shakes their head. The conversation moves on. Tryon, though, was not joking. He went home. He worked out the mathematics. And a few months later in the journal Nature, he published a short paper. Its title was a question: is the universe a vacuum fluctuation? It was, at the time, less than 3 pages long, and it began, quietly, one of the strangest revolutions in the history of cosmology. Tryon's suggestion rested on a simple, almost outrageous observation. The vacuum, as we saw last section, is not empty. It fluctuates. Particles and antiparticles appear and disappear all the time. In ordinary circumstances, they last for only the tiniest slivers of time, a billionth of a billionth of a billionth of a second, and then they annihilate back into the silence of the field, and nothing is left behind. It is as though the vacuum can, briefly, borrow energy from itself, and must always pay it back. But Tryon noticed something no one before him had quite dared to say out loud. If the total energy of a fluctuation is zero, then it does not have to pay itself back. It can, in principle, last forever. And here is where the mathematics of general relativity, Einstein's theory of gravity, does something quietly extraordinary. Because in general relativity, energy comes in 2 flavors. The energy of matter, of light, of motion, of every ordinary thing that fills the cosmos. That energy is positive. It is the energy you were taught about in school. But there is another kind of energy hiding in the theory, the energy of gravity itself. And the gravitational energy of a system, the energy stored in the mutual attraction of every piece of matter to every other piece, has a strange property. It is negative. It is not zero. It is not almost zero. It is less than zero. It counts in the ledger of the universe as a subtraction from the total, which means if you carefully add up all the energy in the observable universe, all the mass of every galaxy, all the light of every star, all the motion of every atom, and then subtract honestly the negative gravitational energy pulling everything together, the 2 columns almost cancel out. To the best of our ability to calculate it, the total energy of the universe is very close to zero. Take a moment with that. The entire cosmos, every world, every ocean, every mountain, every living creature, every thought you have ever had, every ounce of coffee in every kitchen on Earth, the mass of stars uncountable, the light of galaxies uncounted. And if you total it honestly and subtract the pull of gravity that binds it all together, the answer on the ledger is essentially zero. Which meant to Tryon that the entire universe could, in principle, be a fluctuation of the vacuum that, because it cost nothing on balance, was never obliged to disappear. A hiccup in emptiness that forgot to vanish. For a long time, that was where the idea sat. A short paper. A curious thought. An office hours conversation piece. Elegant but impossible to test, and easy to file under interesting speculation. But in the late 1970s and into the early 1980s, three separate ideas began to circle each other in the halls of physics departments around the world. And when they finally came together, they turned Tryon's quiet suggestion into something almost thunderous. The first idea came from a young American physicist named Alan Guth. In 1980, working at the Stanford Linear Accelerator, Guth was trying to solve a completely different problem. He was worrying about why the universe, at its very largest scales, looks so smooth. Why the microwave background whisper, no matter where in the sky you point your antenna, has the same temperature to a few parts in 100,000. Why regions of the cosmos that, according to the ordinary Big Bang, should never have had time to communicate with each other, look nevertheless like they somehow agreed on how hot to be. His answer, which came to him one long night in December of that year, was called inflation. The idea is this. In the first tiny fraction of a second after the beginning, before the universe was even a trillionth of a trillionth of a trillionth of a second old, something extraordinary happened. Space itself did not simply expand. It exploded in a very specific mathematical sense. It doubled in size, then doubled again, then doubled again. And it kept doubling at a staggering rate for a period so brief that the ordinary word instant is far too long for it. By the time this brief episode of inflation ended, the tiny patch of universe that would become everything we can see today had grown, from something smaller than a proton to something larger than a grapefruit. That does not sound like much, until you realize that a grapefruit-sized region of very hot, very dense vacuum, expanding at the ordinary rate afterwards, is exactly what you need to explain the observable universe. Every galaxy, every star, every atom, every thought. If inflation is real, and there is now a wide body of indirect evidence that it or something very like it must have happened, then the seed of the entire cosmos was almost inconceivably small. Not the size of a city, not the size of a room, not the size of a marble, much smaller than that. So small that quantum mechanics, which we normally reserve for describing the world of individual particles, becomes the relevant tool for describing the entire cosmos all at once, which is a remarkable sentence. The entire universe in its earliest instant was quantum, Not the atoms in it, not the particles inside it, the whole thing. That was the first idea, inflation. The second idea came from a young Ukrainian-American physicist named Alexander Vilenkin. In 1982, working at Tufts University outside Boston, Vilenkin published a short, dense paper called Creation of Universes from Nothing. And in it, he proposed something that, even by the standards of theoretical physics, was extremely strange. He said, in essence, do not think of the universe as a small hot ball sitting inside some pre-existing vacuum. Think of it instead as a wave function, a quantum object, something described by the same kind of mathematics we use for a single electron or a single atom. And ask what that wave function does at its earliest moments. What Vilenkin found was that, if you follow the equations honestly, there is a solution in which the universe does not begin at a singularity at all. It quantum tunnels into existence. Now, quantum tunneling is a real phenomenon. It is one of the most well-tested effects in physics. It is how the sun burns. It is how radioactive atoms decay. It is how the transistors in the device you are listening to this on work. In ordinary quantum tunneling, a particle passes through a barrier it does not have enough energy to climb over, because in the quantum world, position is a probability, and there is a small but non-zero chance the particle simply appears on the other side of the wall. Vilenkin's proposal took that idea and applied it to the entire universe. On one side of the barrier there is no universe, no space, no time, no matter, a state he was careful to call, in his own words, nothing. On the other side there is a small, closed, inflating universe, ready to grow. And the transition between the two, he calculated, has a small but non-zero probability. Just as an electron can tunnel through a wall, an entire universe can tunnel into existence from a state that he was willing to call true nothingness. We should be very careful here. Vilenkin's nothing is not obviously the same as the third kind of nothing we talked about last section. It is a state described by a wave function, and a wave function is itself a mathematical object, obeying certain laws, sitting inside a certain framework of physics. Critics have argued, quite reasonably, that this is not really nothing at all. It is a very sparse something, dressed up in the language of nothingness. Vilenkin himself has been thoughtful about this. He has said, publicly and more than once, that his proposal describes a universe with no pre-existing space or time, but that he cannot claim it eliminates the laws of physics themselves. There is always, in the end, at least a mathematics. Always at least a rule for what is allowed to happen. That subtle honesty is worth holding on to, because it will come back later in a much larger way. The third idea came, a year later, from two of the great names in 20th century physics. James Hartle, an American theoretician working in Santa Barbara, and Stephen Hawking, whose name you almost certainly know. In 1983, they wrote a paper together called simply The Wave Function of the Universe, and in it, they proposed something even more radical than Vilenkin's tunneling. They said, in effect, The problem with asking what happened before the Big Bang is that the question assumes time itself was there, ticking in that moment. But what if, at the very earliest instant of the cosmos, time was not yet fully time? What if it was, mathematically, a fourth spatial dimension? What if the beginning of the universe was not a sharp point in time at all, but a smooth, gentle rounding off? A place where time softens into space, the way the northern hemisphere of the Earth softens as you approach the North Pole. If you were an ant walking on the surface of the Earth and you kept walking north, you would eventually reach the pole. And there, you could not walk any further north, not because there was a wall, not because there was an edge, but because the direction north itself simply ceased to be defined. There is no such thing as 10 miles north of the North Pole. There is no forbidden region above it. There is only the surface, curving gently without a boundary. Hubble and Hawking proposed that the beginning of the universe was like that, not a starting line, not a singular event, not a moment where the equations broke down and something happened. Just a place where time itself, treated correctly by quantum mechanics, curved smoothly to a close. There was no before, not because there was a hidden dark room lurking somewhere behind the beginning, but because the word before at that scale no longer meant anything at all. They called this the no-boundary proposal. Now, all three of these ideas, Tryon's vacuum fluctuation, Vilenkin's tunneling, Hubble and Hawking's no boundary, are different in their mathematics. They come from different intuitions. They lead to slightly different pictures of the early moments, but they share something remarkable. They all suggest that the birth of the universe is not, in principle, a violation of physics. That it might be, in some very carefully defined sense, a natural event, something that could have happened, something that, given the right framework, may even have had to happen. And that suggestion, that the beginning of everything might not need a beginning cause, is what turned Tryon's polite laughter in a 1973 Columbia seminar into decades of serious, difficult, contentious cosmology. In 2012, the physicist Lawrence Krauss published a book called A Universe from Nothing. It was intended for a general audience. It became a bestseller, and it drew, sometimes gently, sometimes furiously, on all three of these ideas. Krauss argued that modern physics can, in principle, describe the emergence of a universe from a starting point that most people would call nothing. Some readers loved it, some scientists praised it, and some philosophers were, quite openly, appalled. The philosophical objection was one that Vilenkin himself had already anticipated. It went something like this. Whatever Krauss and his colleagues were calling nothing in their theories was not really nothing. It had structure. It had rules. It had a mathematics that permitted the emergence of a universe. Real nothing, the philosophical nothing, the third kind, would not permit anything at all, not even the possibility of a fluctuation. Not even the framework in which such a fluctuation could be discussed. The debate has continued on and off ever since, and it may never be fully resolved, because it is not, in the end, a scientific debate about facts. It is a debate about what the word nothing is allowed to mean. But something important is worth noting before we move on. In all of this, in Tryon's paper, in Vilenkin's tunneling, in Hartle and Hawking's smooth curve, in Guth's inflation, in Cross's book, there is one shared assumption, so quiet that people often miss it. They all assume that the vacuum or the wave function or the mathematical framework has an energy, a property, a ground state, something you could in principle measure, something you could compare with observation. And if that assumption is right, if the vacuum really does have an energy that gives rise to universes, then it should also, right now, be shaping the universe we live in. It should be gently pulling or pushing on the space around us. It should be leaving fingerprints in the sky. It should, in one very specific way, be measurable. And when we finally tried to measure it, when we compared what our best theories predicted with what the universe actually shows us, we found something that no physicist has ever fully recovered from. The prediction we made and the reality we observed disagreed, not by a little, not by a factor of 10, not by a factor of 1,000. They disagreed by a factor that no other measurement in the history of science has ever come close to. A factor so large that the standard word wrong feels almost insulting. But before we walk into that catastrophe, take a moment, because the idea we just sat with, that the entire universe might be a quantum event, a fluctuation, a tunneling, a bubble that quietly refused to disappear, is in its way the strangest thought you may hold tonight. Somewhere right now, in the vacuum of empty space between two grains of sand on a beach, or between two atoms in the back of your hand, a small quantum flicker is happening. A brief pretense at a universe that will vanish silently back into the field before you finish this sentence. Ours, in one version of the story, is the one that did not vanish. Does that make you feel small? Does it make you feel chosen? Does it make you feel, in some faint, warm way, extraordinarily lucky? If any of those feelings surfaced in you just now, I would love to know which, because they are all, in their own quiet way, honest responses to a cosmos that may have started as an accident. And now, having sat with the idea, let us walk into the measurement, because a beautiful theory in physics is only ever a beginning. What matters in the end is what the sky says back. And when we ask the sky how much energy the vacuum really carries, when we ask the universe to confirm the numbers our theories had so elegantly predicted, the universe answered, and its answer, the one we are about to sit inside for the next section, is the largest disagreement between theory and observation in the entire history of human thought. There is a phrase that quietly circulates among cosmologists, sometimes at conferences, sometimes in late-night conversations over coffee, sometimes in the small, careful footnotes of technical papers. The phrase is used only for a very specific number, and it goes like this: the worst theoretical prediction in the history of physics. That is not hyperbole. That is not a lively turn of phrase. That is a sober, professional description used by working scientists who spend their days calculating numbers to the 6th decimal place. It is the label they have quietly attached to one specific failure, A failure so vast and so uncomfortable that most textbooks introduce it in a single embarrassed paragraph and then hurry on. We are going to sit with it tonight, slowly, because it may be the most important number in this entire story. To understand where the number comes from, we have to go back to a very old idea, and to one very old, very grudging admission by Albert Einstein. In 1915, Einstein finished his general theory of relativity. It was, and remains, one of the most beautiful pieces of mathematics any human being has ever written down. It describes gravity not as a force pulling objects toward each other, but as a geometry, as the shape of space and time itself, gently curved by the presence of matter and energy. A planet in orbit is not being tugged by an invisible string. It is simply following the straightest possible path on a surface that has been dimpled beneath it by the mass of a nearby star. The equations of general relativity are, in a sense, a set of instructions. Tell me what matter and energy are doing, and I will tell you how space-time curves. Tell me how space-time curves, and I will tell you how matter and energy move. That is the whole theory, in one long, elegant handshake. But when Einstein applied his own equations to the universe as a whole, in 1917, he ran into a problem. According to his mathematics, a universe filled with matter and energy could not sit still. It had to be either expanding or contracting. Something everywhere always had to be happening. Einstein did not like that. Almost no one at the time did. The universe was supposed to be eternal, unchanging, majestic in its stillness. So Einstein added a small extra term to his equations. A tiny push built into the fabric of space itself that would exactly balance the gravitational tug of all the matter in the cosmos and hold everything elegantly in place. He called it the cosmological constant. He used the Greek letter lambda to represent it. 12 years later, Edwin Hubble discovered that the universe was not static after all. The galaxies were moving apart. Space itself was expanding. And Einstein, according to the story his friend George Gamow later told, called the cosmological constant his greatest blunder. He removed it from his equations. For the next 70 years, most physicists quietly assumed that it was zero, that the mysterious little term had never really been needed, that the universe simply did not care about it. And then, in 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, made a discovery that overturned that quiet assumption entirely. They were studying distant supernovae, exploding stars of a very specific kind, so uniformly bright that we can use them as cosmic mile markers, measuring how far away a galaxy is by how faint its supernova appears. They expected to find that the expansion of the universe was slowing down. It had to be. Every galaxy in the cosmos pulls on every other galaxy through gravity. Over time, that mutual tug should quietly break the expansion. Perhaps not enough to reverse it, but enough at least to slow it. Instead, the supernovae told them the opposite. The universe was not slowing down. It was speeding up. The distant galaxies were flying apart faster today than they had been billions of years ago. Something was pushing the cosmos outward at every scale against the pull of all the matter it contained. Something was accelerating the expansion. For that discovery, Perlmutter, Schmidt, and Rees would share the Nobel Prize in Physics in 2011. And the something they had discovered, that mysterious outward push, was given a placeholder name that has stuck ever since: dark energy. What is dark energy? That is the question we are still living inside, more than 25 years later. But the simplest possible answer, the one that fits most of the data, and that has been the working assumption of cosmology for most of that time, is that dark energy is exactly the cosmological constant Einstein wrote down and then abandoned. A gentle, uniform, unchanging outward push built into every cubic centimeter of space itself. And here is where the story begins to bend quietly in on itself. Because a uniform energy filling every point of empty space sounds very familiar. It sounds, in fact, like the vacuum energy we spent the last 2 sections discussing. The energy of the humming, seething, restless quantum fields that fill the cosmos. The energy revealed by the Casimir force. The energy that lights the stars. Could the cosmological constant and the vacuum energy of quantum field theory be the same thing? For a while, in the late 20th century, that was one of the most hopeful ideas in all of cosmology. It would be so tidy. 2 mysteries resolving each other in a single elegant equation. The strange outward push of the universe and the strange background hum of empty space revealed to be one and the same phenomenon. There was only one problem. When the calculations were finally done, honestly and carefully, the 2 numbers did not match. They did not match by a little. To do the calculation, physicists take their best theory of the quantum vacuum, quantum field theory, which has otherwise been tested to some of the most precise agreements between prediction and measurement anywhere in science. And they ask, in effect, add up the zero-point energy of all the quantum fields that fill space, sum over every possible mode of vibration, up to the highest energy at which we trust the theory. Give us a number. The number that comes out is enormous. The number that comes out of astronomical observation. The number we actually measure by watching the expansion of the universe is very, very small. The ratio between them, between what the theory predicts and what the sky actually shows us, is not a factor of 2 or 10 or 1,000. It is, in most standard estimates, a factor of 10 to the power of 120. 10 with 120 zeros after it. I want to give that number a moment because human minds are not built for it. If you laid out 1 atom for every zero in a single line, 1 atom per zero, that line would run across almost every galaxy we have ever catalogued. If you gathered together every grain of sand on every beach and every desert on Earth, you would still be nowhere near it. If you counted every atom in your body, and then in every human body that has ever lived, and then in every planet, and then in every star, in every galaxy in the observable universe, you would still, at the end of that unimaginable inventory, be less than 100th of the way there. 10 to the 120th power. That is the ratio between what our best theory of the vacuum says empty space should be doing, and what the actual sky above your head is doing. If the theory were right, the vacuum energy would be so overwhelmingly large that the universe would have torn itself apart in the first tiny fraction of a second after its beginning. Space would have expanded so violently, so instantly, that no atom could have ever formed. No star could have ever burned. No galaxy could have ever cooled. No small warm planet could have ever gathered around a small warm star. There would be no you, no me, no listener anywhere in the cosmos wondering about any of this. Instead, we live in a universe where the cosmological constant is almost, but not quite, zero. A universe where the expansion is accelerating, but so gently and so patiently that atoms and stars and galaxies and thoughts have had all the time they needed to form. The prediction is off by a factor of 10 to the 120. The prediction should have destroyed us, and yet here we are. Physicists have a name for this discrepancy. Some call it the cosmological constant problem. Some call it the naturalness problem. Some, more bluntly, call it the vacuum catastrophe. Steven Weinberg, one of the great theoretical physicists of the 20th century, wrote a famous review of the problem in 1989, in which he called it a bone in our throat, a thing we cannot swallow and cannot cough up. Others have been less polite. There is a widely quoted line, attributed sometimes in one form, sometimes in another, that this is the largest disagreement between theory and experiment in the entire history of science. Now, some physicists gently will point out that the number 10 to the 120 is a little unfair. It is the ratio of energy densities, which grows very fast when you translate from a difference in mass scale into a difference in units of energy per volume. If you express the mismatch as a difference in the underlying mass scales, rather than in the raw energy densities, it comes out to something more like 10 to the 30 or 10 to the 50, depending on which cutoff you use, which theoretical assumptions you make, which quiet, careful accounting decisions you allow yourself. But even in the kindest, most generous version of the accounting, we are still talking about a disagreement of 30 orders of magnitude, 30 zeros, which is still, by a very wide margin, larger than any other failed prediction in the entire history of physics. Sit with that for a moment. If your car's speedometer were off by a factor of 10 to the 30 and you thought you were driving at the speed limit, you would in fact be moving faster than the speed of light through every galaxy in the observable universe, many times over in every fraction of a second. That is the scale of the disagreement we are talking about, in the most conservative version of the story. In the version physicists reach for when they want to look calm, something, somewhere in our understanding of the vacuum is very deeply wrong. Now, to their enormous credit, physicists have not simply thrown their hands up and walked away. Over the past 40 years, some of the brightest minds in theoretical physics have proposed possible solutions, possible ways of hiding, canceling, or reinterpreting this monstrous discrepancy. Let us walk through a few of them briefly, not to master the mathematics, but to feel the shape of the desperate search. One family of ideas involves symmetries, deep, hidden mathematical symmetries in the laws of physics that might cause the enormous vacuum contributions from different fields to cancel each other out almost perfectly. The most famous of these is called supersymmetry. In an exactly supersymmetric universe, the vacuum energy contributions from ordinary particles are exactly balanced by contributions from their heavier, hypothetical supersymmetric partners. Every electron would be balanced by a heavier partner called a selectron. Every photon by a heavier partner called a photino. And the vacuum energy would sum cleanly to zero. There is only one problem. We have looked very hard for supersymmetric partners in the Large Hadron Collider at CERN, in cosmic ray experiments, in deep underground detectors, and so far we have not found them. If supersymmetry exists in nature, its partners are much heavier than we initially hoped, which makes the cancellation much less clean, which brings the vacuum energy problem back in a slightly softer form, but still overwhelmingly large. Another family of ideas involves what is called the anthropic principle. It is a strange, almost circular argument, and Weinberg himself was one of its earliest, most careful advocates. The reasoning goes like this. Perhaps there are many universes. Perhaps the vacuum energy takes different values in different universes, distributed across some vast underlying landscape of possibilities. In most of those universes, the vacuum energy is enormous, and no structure ever forms. In a very small fraction, by sheer accident, the vacuum energy is small enough that atoms, stars, and galaxies have time to appear. And any conscious observer asking why the vacuum energy is small could only ever find themselves in one of the rare universes where it is, because they could not exist in the others. It is a clever argument, and it is not technically wrong. But it also feels to many physicists like a quiet form of surrender, like an answer that stops asking why the number is what it is and starts merely explaining in retrospect why we are here to notice it. Some love the idea, some find it deeply unsatisfying. Almost everyone at 3 in the morning admits it is uncomfortable. There are other proposals, modifications of general relativity, in which the cosmological constant is not really a constant at all, but a dynamical field. The trace-free version of Einstein's equations, in which the vacuum energy simply does not gravitate the way we thought. Ideas involving quantum gravity, holography, extra dimensions, subtle cancellations we have not yet noticed, whole new symmetries we have not yet dreamed of. None of them at present have been confirmed, and none of them at present have been ruled out, which is why the vacuum catastrophe remains, decades later, exactly what it was when it was first noticed. A quiet, persistent, unresolved embarrassment sitting at the heart of our best description of the universe. But here is the twist. The one that turns this entire story from an old, familiar problem into something new and something more disturbing. For most of the past 4 decades, physicists have consoled themselves with a certain kind of hope. Yes, the vacuum energy calculation is wrong by an outrageous factor. Yes, we do not understand where the discrepancy comes from, but at least, they said, the thing we are trying to explain, the observed cosmological constant, is a fixed number, a stable target, a single, unchanging value, sitting patiently in the sky, waiting for a future theory to catch up with it. If dark energy were truly a cosmological constant, if it were simply the vacuum energy of empty space, made to work by some future breakthrough in theoretical physics, then at least the observed value would be reliably the same everywhere for all time, something a future genius could aim at and hit. But in the last 2 years, the data has begun to say something very different. 3 of the largest, most sophisticated observational efforts in the entire history of astronomy have been quietly turning their eyes on the cosmos, measuring, with unprecedented precision, the actual behavior of dark energy across the history of the universe, comparing that behavior with what the standard model predicts. And what they are finding together from 3 independent directions is unsettling in a way that no textbook has yet caught up with, because it seems more and more that dark energy may not be constant at all. The number the physicists have been trying to explain for 40 years. The value at which we have been aiming our theories may itself be shifting, slowly, quietly, in ways that the old vacuum energy story cannot easily accommodate, which means the vacuum catastrophe may not be a single stubborn number waiting for a single clever explanation. It may be a symptom of something much deeper, something we have not yet named, something that suggests we have been measuring and mismeasuring the very fabric of the cosmos for longer than any of us realized. Before we go there, though, let this settle for a moment. Because you have just been told a true, sober, professional fact. In one very precise sense, humanity's most rigorous prediction about the nature of empty space is, at minimum, off by more than the number of atoms in the observable universe. And in the harshest accounting, it is off by more than the number of atoms squared. And that failure has been sitting in our best theory of the world for almost half a century. If humanity's sharpest instrument for describing reality can be that wrong about the thing our universe is supposedly made of, how confident should we really be about any story we tell about the beginning, about what the vacuum is, about what nothing means, about whether the question we started this whole night with has any well-defined answer at all? I would love to know, in a quiet moment, whether that thought steadies you or shakes you. Whether the immensity of the mistake makes you trust science more because it is willing to admit its own failures, or less because it is willing to be that far off for that long without a solution. There is no wrong answer, just the honest response your mind lands on. And now, having seen the crack, we are going to look at the wider fractures. Because in the last 2 years alone, 3 independent windows on the cosmos have begun to show us something the old textbooks did not prepare us for. A universe that is not quite behaving the way our theory says it should, in 3 different, independent, disconcerting ways. Let us go and look at them together. There is a comforting story that most of us are taught when we first learn how science works. Data comes in. Theories are tested. When a theory fits, we keep it. When a theory fails, we set it aside. The process is patient. The process is orderly. The process is quiet. That story is true in a slow and long-term sense. But it does not capture what it actually feels like to live inside a science that is, right now, at this very moment, beginning to strain against its own foundations. And that is what is happening in cosmology in 2024 and in 2025 and in the months during which you are listening to this. For most of the last quarter century, cosmologists have worked inside a single beautifully successful model of the universe. Its name is a mouthful. Lambda cold dark matter, or more compactly, lambda CDM. The lambda, that Greek letter Einstein used, refers to the cosmological constant, the dark energy, the unchanging outward push we discussed in the last section. Cold dark matter refers to the invisible, slow-moving stuff that outweighs ordinary matter in the universe by roughly a factor of 5. And together, the two ingredients, along with a small dash of ordinary matter and radiation, make up the recipe from which the standard model of cosmology cooks the entire history of the cosmos. For 25 years, that recipe has worked. Not perfectly, but well enough. Well enough that when astronomers plug it into their supercomputers and simulate the universe, they get out a cosmos that looks a lot like the one we see. The right cosmic microwave background, the right distribution of galaxies, the right web of filaments and voids, the right balance of matter and energy, adding up to a spatially flat cosmos, 13.8 billion years old. But in the last 2 years, that quiet consensus has begun to strain, not in one place, not from one instrument, but from 3 completely different directions, 3 completely different techniques, 3 completely different scientific communities, working on 3 completely different questions. And all of them, quietly and independently, are pointing at the same uncomfortable possibility. The concordance model of cosmology may be, in some deep and important way, wrong. Let us walk through the 3 cracks gently. The first crack comes from a machine called DESI. That stands for the Dark Energy Spectroscopic Instrument. It is a remarkable piece of engineering, sitting on top of a 4-meter telescope at Kitt Peak National Observatory in Arizona. Its job is to measure, one by one, the distances to millions of galaxies across the sky. Not tens of thousands, not hundreds of thousands, millions. And by measuring the pattern of how galaxies are distributed at different distances, at different eras in cosmic history, DESI is quietly assembling the largest 3-dimensional map of the universe ever made. The reason this matters for our story is that the pattern of galaxies carries the fingerprint of dark energy. As the universe expands, dark energy stretches the space between galaxies. And the way that stretching evolves over time, whether it stays constant, whether it grows, whether it slowly weakens, tells us something very precise about what dark energy actually is. If dark energy is Einstein's cosmological constant, if it is simply the unchanging outward push we discussed, then the pattern of galaxies should evolve in one very specific way described by a single fixed number. If dark energy is something else, if it changes with time, if it is a dynamical field, not a constant, then the pattern should evolve differently. In 2024, DESI released the results of its first year of data. In 2025, it released the second, larger, more precise release. And in both, the same quiet signal has emerged. Dark energy does not appear to be behaving as a constant. It appears to be evolving, weakening ever so slightly over cosmic time. The statistical significance of the signal depends on which supernova dataset you combine with the DESI measurements. But by the 2025 release, when DESI's baryon acoustic oscillation data was combined with the standard cosmic microwave background maps from Planck, and with modern supernova catalogs, the disagreement with a simple cosmological constant reached somewhere between 2.5 and just under 4 standard deviations. In the language of physics, that is not yet a definitive discovery, but it is very much not nothing. It is, as some cosmologists have quietly put it, a statistically loud whisper. If DESI is right, then dark energy is not a cosmological constant, which means the target we have been aiming our theories at for the past 40 years is not the target we thought it was, which means the vacuum catastrophe of the last section becomes even stranger, because we may have been trying to explain the wrong number all along. That is the first crack. Now let us walk to the second. The second crack comes from a telescope you have almost certainly heard of, the James Webb Space Telescope, launched at the end of 2021. Cooled to almost absolute zero, sitting 1,000,000 miles from Earth at a quiet gravitational parking spot known as the second Lagrange point. Its mission, among many others, is to look further back into cosmic time than any instrument human beings have ever built. And it can. James Webb sees the universe in infrared light, which means it can catch the light of galaxies whose original visible glow has been stretched by billions of years of cosmic expansion into wavelengths that ordinary telescopes cannot detect. It can look back to a time when the universe was less than 500 million years old, which is, in the timescale of the cosmos, when the universe was practically a newborn. Now, the standard picture before Webb was very clear. In those earliest few 100 million years after the Big Bang, galaxies should have been small, faint, simple, structureless, little bright clumps of the first stars, quietly gathering themselves into shape slowly over hundreds of millions of years. The first galaxies were supposed to be embryonic. The great spiral wheels and glowing ellipticals we see today should have taken billions of years to assemble. Then Webb turned on, and what it began to see was not what the standard picture predicted. There was GNZ 11, a galaxy first identified by Hubble and now studied in exquisite detail by Webb. It exists at a time when the universe was only about 430 million years old, and it is far, far too massive and far too luminous for such an early age. Its spectrum shows chemistry and structure and star formation activity that our models struggle to explain. There was CERS 2588, a galaxy observed at a similar era, roughly 400 million years after the Big Bang. Massive, metal-rich, already forming stars at a rate that, according to conventional models, should not have been possible. And in early 2025, there came the galaxy nicknamed the Big Wheel, a galaxy from within the first 2 billion years of the cosmos that already possessed a mature spiral structure. A great glowing, disc-shaped wheel of stars, with arms and a rotation pattern reminiscent of our own Milky Way, which, according to the standard picture, should have taken far longer to organize itself into that shape. None of these individual galaxies on their own would be enough to break a theory. Astronomy is full of surprises. Every generation brings a few objects that were not predicted. But Webb is not showing us 1 or 2 odd galaxies. It is showing us a population, a statistical excess, a pattern of galaxies at very high redshifts, at very early epochs, that are systematically more massive, more luminous, and more structured than the standard model of cosmology predicted. By 2025, deep survey programs like JADES had cataloged thousands of galaxies at the highest redshifts ever probed. And the bright end of the galaxy population, at redshifts greater than 10, is measurably more numerous than pre-Webb predictions allowed. There are conventional explanations still on the table. Perhaps early star formation was more efficient than we thought. Perhaps the first stars were much more massive and much brighter than their descendants. Perhaps there is a subtle systematic error in how we translate what Webb sees into stellar mass. These are serious proposals, and they are being tested carefully. But another possibility, quietly discussed in professional papers, is that the standard model of cosmology itself needs to be modified. That the timeline of structure formation in the early universe cannot be reconciled with lambda CDM without pushing at least one parameter, or one assumption, harder than it comfortably wants to go. That is the second crack. Now let us walk to the third. The third crack is called the Hubble tension, and it is, in some ways, the most stubborn and the most quietly maddening of them all. Recall that the Hubble constant, that number Edwin Hubble first hinted at in 1929, is a measure of how fast the universe is expanding right now. In the modern era, we have 2 very different ways of measuring it. The first way is to look at the very early universe, to measure the tiny temperature fluctuations of the cosmic microwave background, and to fit the standard model of cosmology to them. The Planck satellite, up through 2018, and now updated analyses, give us a value of the Hubble constant of about 67.4 kilometers per second per megaparsec. Give or take a few tenths. The second way is to look at the local universe, to build what is called a distance ladder, starting with the nearby stars whose distances we can measure directly, moving out to nearby galaxies, whose distances we can measure with pulsating stars called Cepheid variables, and then moving farther out with exploding stars, the type Ia supernovae. A team called SH0es, led by the same Adam Rees who helped discover dark energy, has been refining this distance ladder for more than a decade. And their most recent, most careful measurements give a value of the Hubble constant of about 73 kilometers per second per megaparsec. Give or take about 67.4, 73. That does not sound like a huge difference, but in the language of cosmology, given the precision of both measurements, it is enormous. As of late 2025, the disagreement between the two methods sits at roughly 5 to 6 standard deviations. In statistical terms, that means the probability that the mismatch is due to random chance is far smaller than 1 in a million. For years, most cosmologists assumed the tension would go away. Someone would find a systematic error, a subtle bias in how one team calibrated their Cepheids, a missed effect in how the other team modeled their microwave background. Someone would notice a mistake, and the two numbers would drift together and the puzzle would close. But it has not closed. Instead, it has hardened. In 2023, the James Webb Space Telescope reobserved many of the Cepheid variables that the local distance ladder relies on, and confirmed that the earlier Hubble Space Telescope measurements were essentially correct. In 2025, an independent method known as time delay strong lensing, which uses the way massive galaxies bend the light of distant quasars, released fresh results from a collaboration called TDCOMO, and further supported the tension. Independent measurements from gravitational waves are beginning to add their own voice to the chorus. Different techniques, different assumptions, different systematic errors, and yet the split remains. The universe, in some quiet, insistent way, is telling us that its expansion looked one way when it was young and looks a different way today. And no amount of careful bookkeeping seems to make the difference go away. 3 cracks, DESI, whispering that dark energy is not constant. Webb whispering that structure formed earlier and more vigorously than we thought. And the Hubble tension, whispering that the very rate at which the universe is expanding cannot be reconciled between the early and late cosmos inside the current model. 3 whispers from 3 different windows on 3 different aspects of the cosmos, all pointing in the same direction, all saying, gently but firmly, that something in our best description of the universe is not right. Cosmologists are, as of this moment, in the middle of a very serious professional argument about what to do next. Some believe the standard model can be saved, with only modest additions. A new field called early dark energy that appears briefly before the microwave background formed and then fades away. A slight modification of gravity at the largest scales. A rethinking of the properties of neutrinos. A subtle change in how we calibrate the microwave background. Others believe the model needs a deeper overhaul, that the vacuum catastrophe and the DESI results and the JWST results and the Hubble tension are not 4 separate problems. They are 4 faces of a single underlying misunderstanding. Something we have been getting wrong from the very beginning about what the vacuum is and how it evolves and what dark energy really represents. If that second, more radical view is right, then the story we have been telling ourselves about the birth of the universe may need to be almost completely rewritten. Not because our observations are wrong, not because our mathematics is wrong, but because the framework inside which we have been asking the questions, the framework of a cosmological constant sitting quietly inside a fixed vacuum, may not be the right framework at all. Which brings us, gently, to the strangest thought we have not yet dared to say out loud. Perhaps we have been measuring the very fabric of nothingness itself wrong, not by a small factor, not by a subtle bias, but at the level of what nothingness even is. Perhaps the vacuum we thought was a stable, quiet stage, holding still while dark energy sat upon it, is not stable at all. Perhaps it is a slowly changing thing, a field evolving over cosmic time, a property of the universe that is doing something we do not yet understand. Perhaps the reason our best prediction of the vacuum energy is off by such a monstrous factor is not that our arithmetic is bad. It is that the thing we are calculating and the thing the universe is doing are not the same kind of object. We have been trying to measure nothing, and we have not yet succeeded because we have not yet understood what nothing was doing while we were watching it. Now, whether the cosmology of the next decade will confirm this reframe, or will save the standard model with some clever new idea, is not something we can know tonight. What we can know is that, right now, at this very moment, the science is genuinely in motion. 3 separate telescopes, sitting in the desert and above the atmosphere and in laboratories around the world, are telling us that our best story about the universe is not quite finished. That is not, in the end, a discouraging story. It is, in a strange and beautiful way, the most hopeful thing you can hear about a science. Because a science that has fully solved its universe is a science that has stopped listening. A science that has begun to feel its own foundations tremble is a science that is still awake, still curious, still worthy of the cosmos it is trying to describe. Sit with that for a moment and ask yourself something honest if you would. If 3 of the largest telescopes ever built are quietly telling us that the universe is not behaving the way our best theory says it should, do you find yourself trusting the theory more and waiting for the observations to be explained? Or do you find yourself trusting the sky more and waiting for the theory to change? There is no right answer, but your instinct, the one that surfaced when I asked, is probably telling you something quiet and true about how you relate to human knowledge. I would love to know which way you leaned when the question landed. Because now, having seen the cracks, having felt the model bend beneath the weight of the sky, we come to the final, strangest, most quietly liberating possibility of all. The possibility that the question we began this entire night with, the one we have been slowly circling for 2 hours, may not have an answer, not because we are too small to find it, not because our instruments are too clumsy, not because our mathematics is too primitive, but because the question itself was built on a hidden assumption. An assumption so quiet, so old, so deeply embedded in the way human minds are shaped, that we have almost never thought to question it. The assumption that there was ever a beginning at all. Let us walk into that together in the last movement of this long night. Let us walk back briefly along the road we have traveled tonight. We began with a picture, A single bright dot sitting in a great empty dark, a firework in a waiting sky. And we watched together as that picture came quietly apart in our hands. There was no dark room. There was no outside. There was no explosion into a stage that had already been built. There was only the stretching everywhere of the stage itself. Then we walked into the Word. The small, quiet Word we had been carrying without noticing. Nothing. And we found that it was not one word, but at least three. That the empty jar in the quiet corner of a laboratory is not empty. That the vacuum in the deepest theories we have is a restless humming thing. That two uncharged metal plates held in a room stripped of all matter will still push toward each other, gently, because of the invisible energy in the space between them. Then we met an idea. A small, strange idea, first spoken out loud in a seminar in 1973 and quickly followed by others. That the entire universe might be a fluctuation of the vacuum, a ripple in emptiness that, because it cost nothing on balance, was never obliged to disappear. That our cosmos might be, in the strictest mathematical sense, an accident that forgot to correct itself. Then we walked into the catastrophe. The prediction that empty space should have obliterated itself in the first tiny fraction of a second after its beginning. The largest disagreement between theory and observation in the entire history of science. A discrepancy so vast that, in its most honest form, it is measured not in factors of 10, but in factors of 10 to the 120th power. And yet somehow here we are, listening to each other in a quiet room on a small warm planet orbiting a small warm star. And then we saw the cracks. 3 telescopes, 3 techniques, 3 separate windows on the cosmos. Each of them, quietly and independently, whispering that our best story of the universe is not quite finished. That dark energy may not be constant. That galaxies formed too quickly. That the expansion of the universe looked one way when it was young and looks another way now. That we may have been measuring nothingness itself wrong, at some very deep level that we do not yet understand. And so, at the end of that long walk, we arrive finally at the question we started with. Can a universe be born from nothing? And we notice, if we are honest, that we do not know how to answer it. Not because we have not thought hard enough, but because every attempt to answer it stumbles immediately on the same small, quiet problem. We do not know what the question is really asking. If we mean, can a universe emerge from the humming vacuum of quantum fields, then the answer in some of our most careful theories is yes. Perhaps, under certain conditions, in certain formulations. If we mean, can a universe emerge from a state with no matter, no radiation, no fields turned on, then the answer becomes stranger. Because it is not clear such a state exists in nature. It may be a mathematical suggestion, a limit that reality never quite reaches. And if we mean, can a universe emerge from absolute philosophical nothingness? No space, no time, no laws, no mathematics, no possibility of possibility, then no theory we have is really up to the question. Because every theory we have begins by assuming a mathematics inside which the story is allowed to happen, which suggests, gently, something that a few careful physicists and philosophers have been quietly saying for a long time. Perhaps the question was never fully coherent to begin with. Perhaps the word nothing, in the third and strictest sense, is not really a description of a state that could ever exist. Perhaps it is a shape our language makes when it tries to imagine the removal of everything, without noticing that the removal itself is a something. Perhaps the question, can a universe come from nothing, is a little like the question, what is north of the North Pole? We spent a moment with that idea already when we met James Hartle and Stephen Hawking, but let us return to it now more slowly. If you were standing on the surface of the Earth and you began to walk north, you could keep walking and walking and walking, past forests, past ice, past the last towns and the last science stations. Eventually, if you were patient enough, you would arrive at a point on the Earth called the North Pole. And there, if you turned in any direction, every direction would be south. There is no north of the North Pole. There is no forbidden region hidden above it. There is no dark room where the surface of the Earth was not permitted to reach. There is only the surface, curving gently to a close. Hartle and Hawking suggested that time itself, at the very beginning of the universe, behaves in a way that is mathematically similar to that. That if you traced the history of the cosmos backwards, you would not eventually arrive at a sharp line labeled the beginning. You would arrive at a place where time softens into space, where the direction we call before quietly ceases to be defined, where the question, what came earlier, no longer has anything for its words to refer to. There is no earlier than the earliest, not because there is a wall, not because there is a mystery beyond it, but because the concept of earlier at that scale gently dissolves. There is only the surface of time, curving to a close. If that is right, and it is one of the most seriously discussed possibilities in modern cosmology, then the question we started with may not simply be unanswered. It may not be a real question at all. It may be a shape our minds have been trying to fit onto a cosmos that was never obliged to have that shape. A ghost cast by human language onto a universe that does not need language. And here is where a certain calm begins to arrive. Because if there was no true beginning, then there was no true nothing that came before it. And if there was no true nothing that came before it, then the question of how something came from nothing does not describe a real event in the history of the universe. It describes a confusion in the history of our thoughts about the universe. That is not a small thing. It is not a philosophical dodge. It is a very old, very careful suggestion, made by very serious people, that some of the deepest questions of cosmology may be, at their root, a mismatch between the way the cosmos actually behaves and the way our minds insist on structuring it. And there is a strange comfort in that, because we, you and I, are creatures who were built for a particular kind of story. We are creatures of before and after, of cause and effect, of birth and death. We navigate the world with those tools, and we could not survive without them. When you cross a street and you check for cars, you are trusting cause and effect. When you plant a garden in spring, you are trusting before and after. When you love someone and you fear their absence, You are trusting the entire architecture of time. These are good tools. They are the tools of a species that evolved on a small planet, in a certain slice of time, at a certain scale, in a certain kind of environment. They are the tools you needed to see the shape of a lion in tall grass, and the tools you needed to remember where the water was in a dry season. But there is no promise, anywhere in the cosmos, that these tools should scale. There is no promise that the concepts of before and after, which serve us so well for keeping appointments and raising children and building bridges, should also apply to the origin of the entire universe. There is no promise that the concept of a cause, which we use to understand thunder and rain and the flu, should also apply to whatever is happening at the very edge of the equations, where time softens into space. We reach for those tools in the small hours of the night when we ask what came before the Big Bang. We reach for those tools when we ask how something can come from nothing. And when the tools fail, we feel that failure as a kind of vertigo, as though the world itself has slipped. But it is not the world that has slipped. It is the tool. The cosmos, gently, has never claimed to be a story of before and after all the way down. It has never promised that the shape of our language should be the shape of its truth. And when we take a slow, patient walk into the very earliest instant of the universe, we find, quietly, that some of our sharpest questions dissolve, not because they are being answered, but because they were never really questions the cosmos was obliged to hear, which brings us at last to a very small thought about you. You are, right now, listening to a voice. Somewhere in a room, on a planet, in a galaxy, inside a universe that may or may not have had a beginning, made of atoms that were forged in the cores of stars that have long since died, assembled by biology so fragile that a single stray photon at the wrong frequency could damage a strand of the DNA that holds you together. Sitting inside a cosmos so vast that light itself, moving at the fastest speed our physics permits, would take billions of years to cross even a modest portion of it. You are, by any honest accounting, a temporary arrangement, a quiet complication of matter that has organized itself into a shape that can wonder. And yet, tonight, you have been wondering about something so far outside your ordinary life, so far above the size of your kitchen, so far below the depth of your language, that the ordinary word wondering feels almost insulting to the act. You have been asking, in the calm of your evening, whether a universe can come from nothing. You have been sitting patiently with the strangest possibilities modern physics can offer. You have been holding contradictions that would have terrified the sharpest minds of any previous century. And you have been doing all of that willingly, in the last hours of a day that has probably otherwise been ordinary. That is not a small thing. That is not something you should let pass unremarked in your own life. The cosmos is enormous. It is old. It is quiet. It is stranger than any of our stories. And it produced, at some quiet moment in a certain corner of a certain small galaxy, a creature that can turn its attention back on the whole of it. That can ask, with genuine humility, where any of this came from. That can sit at midnight with the possibility that the question does not have an answer and not run from that thought, not despair at it, not need to fix it. You are that creature. And whatever nothing turns out to mean in the end, and whatever the vacuum turns out to be doing, and whichever way the DESI and JWST data eventually leads us, and whatever new instrument reveals its next quiet fingerprint on the sky, you will be part of the very small chain of minds across the very long history of thought that took the time to ask. That is not consolation. That is not a decoration. That is, in a strange and quiet way, a kind of belonging. You are not standing outside the universe, looking in through a keyhole at a story about its birth. You are inside it. You are, in some literal and unimprovable sense, the universe becoming aware of itself, for a small and lucky window of time, in a small and lucky corner of its evening. Before we close, if you have made it this far, and if you have found this kind of slow, patient walk into the cosmos worthwhile, a like or a subscribe genuinely helps this channel keep going into the dark like this. It is a small gesture on your side. It is an enormous gift on ours. Thank you for sitting with all of this tonight. And one last question, if you have the patience for it. If the universe has no true beginning, if there was never a moment of first breath, if the question of what came before is a shape our minds make, not a shape the cosmos ever agreed to, does that thought make you feel more alone in the immensity? Or does it make you feel somehow more at home? There is no wrong answer. But I would love to know where your mind lands when the whole long night finally settles. And so, at the end of this walk, we do not have a tidy resolution to give you. We do not have a clean answer to the question we asked at the beginning. We have instead something that may be worth more than an answer. We have a set of gentler assumptions. We have permission to sit with a question that may not be a question. We have the quiet knowledge that our best theories and our most patient telescopes and our sharpest minds are still, right now, tonight, working carefully in the dark, trying to understand a cosmos that has never once promised to be understandable. The story is not over. The story is just very old and very deep and very patient. And you have joined it for a night and given it your attention. And that is a small holy thing in a cosmos that did not have to produce attention at all. So rest now. If it is late wherever you are, let the question sit. Let the numbers cool. Let the images of empty space and quiet vacuums and telescopes on cold desert mountains and small metal plates pushing gently toward each other in a laboratory drift into whatever comes next for you tonight. There is no ceiling above you that you have to climb. There is no floor beneath you that you have to guard. There is no beginning waiting to be located. There is only the slow, quiet, patient cosmos unfolding itself around you as it has always done. Sleep well under a sky with no edge, no beginning, no floor beneath it, and no need for any of them. Good night.